Okay, today we will be talking about molecules, compounds, and chemical equations. So let's get started. In the world, there are 7 what we call diatomic elements. So there are elements on the periodic table that exist as diatomic molecules. So they're chemical species that are made up of the element, um, but are chemically bonded together. So the 7 diatomic elements, um, 7 diatomic elements are, we're going to have hydrogen, H2, nitrogen, N2, fluorine, F2, iodine, I2, chlorine, CO2, and then oxygen, O2, bromine, Br2. Okay? So those are the 7 diatomic elements. A nice way to remember this is this kind of mnemonic here. Please, sorry, not please. What I meant to say is have no fear. Drink an ice cold beer. Or, a beverage for the last diatomic element. So hydrogen, H, nitrogen, chlorine, oxygen. Where is oxygen actually? Huh. There wasn't anyone. I see. Iodine. And this one would be chlorine and oxygen here, and then bromine here. Okay, so that's a helpful mnemonic, but if you just go over them a few times, you probably can get them memorized. So I would recommend that. So there's 2 polyatomic elements that exist in not as a single atom, but they have multiple atoms in their structure. So for example, sulfur, we don't just see a sulfur atom, we see S8. And then phosphorus, we don't see just a phosphorus atom P, we see P4. Okay. So now that we know kind of these chemical compounds, we know matter is composed of multiple these chemical compounds, but they can exist in 3 different states of matter, which are the predominantly forms of matter that we see in daily life or in the world today. We don't really see any other types as common. Like there is plasma and there's a new form of glass, I think, called liquid glass. But those are not very mainstream. Well, I don't say mainstream. They're not as common as these other 3 types. So solid, liquid, and gas. So after this lecture, there'll be some questions about the lecture, so participation questions. So make sure you do them, because if you don't watch the videos and do the participation questions, you can't move on to the next lecture. So these mechanisms are kind of designed to help work through the course in an efficient way. Okay, so you're not playing catch up. Okay. So this activity will actually change. So I'm just going to cross this out. Just remember to do the participation questions. I may ask about some properties of solid, liquid, or gases, but so that may come up on the participation questions. Okay. What are allotropes? Well, allotropes are 2 different forms of the same substance. So even though, say an element can exist in one form, versus another form, those are what allotropes are. So, if we had sulfur, for example, maybe it can exist as um, its arrangement of the sulfur atoms is one way, while the arrangements of the sulfur atoms in a different substance is a little bit different, but they're still called sulfur. So when we have a situation like that, we call them allotropes. And two examples of allotropes are carbon, or example of a substance having or an element having an allotropes is carbon. So we have two different forms of the same substance. Okay, like that. So diamond and graphite, they are allotropes of carbon. So of the carbon element, the element carbon. So we see here two different forms. One is diamond, so a very sturdy, very rock hard substance, very lustrous, very rare, very pretty, very expensive. And next, the other form we have is graphite, where it's this material that we can use as a writing utensil and has some interesting properties. Graphite, great conductor of energy, heat, and electricity, which is kind of strange given that carbon is not a metal. So graphite has some interesting properties. And you see here, they're very different forms of carbon, very different properties, but they are composed of the same element, carbon. Okay. So there are two types of bonds present, two types of bonds in chemical compounds, usually covalent and ionic. So ionic compounds, some properties of ionic compounds, they have high boiling points. So we have high boiling points, high boiling points, high melting points, and they're usually solids at room temperature. Usually solids at room temperature. And one thing about these ionic compounds are very strong because they're composed of ionic bonds, or they are bonds made from ions. Ions attract each other. Okay, so you have oppositely charged ions being the main bonding force in these type of compounds, and then covalent compounds are the opposite. So covalent compounds, they have low boiling points, and melting points, low melting points. And these are usually gases. Okay, so they're usually gases at room temperature. So the main force here is that you have covalent bonds. Covalent bonds where electrons are shared. So the electrons are shared in these compounds, and that kind of gives rise to wider low boiling points, low melting points, because the forces of attraction in these compounds between different molecules are typically lower because there's no ions involved. So there's no like full-on negative or positive charge. So there's less energy interaction. So that's why you get the lower boiling points and melting points. All right, so those are two types of compounds that we see for elements. Two types that elements form. Either you have ionic compounds or covalent compounds. Okay, so example here we have a good example of this is sodium chloride and oxygen. Very two different compounds. Sodium chloride is a solid here with a melting point of around 800 degrees and a boiling point of 1,465 degrees Celsius. So when you add salt to when you cook, maybe like you boil some noodles, add some salt, or whatever dish you may make, the salt usually kind of vanishes into the boiling water, right? Well, we're not actually melting the salt, we're just dissolving it. So it becomes part of the water. It becomes part of the solution. Now, a solution, you have water molecules surrounding the salt ions, so sodium chloride ions, and that's what brings it into solution. That's why you can't really see the tiny salt particles anymore. And it usually causes water to kind of boil up and cause, if you put in too much salt, it may eventually boil too much because there's some energy being released there, and that causes somewhat the temperature of the water or the temperature in the water to kind of increase, and that will cause the water molecules to kind of move a bit faster. So that's a kind of a chemical reaction there. Okay, and then in this structure here, we zoom in here. This is the actual structure of sodium chloride. You see here it's composed of these sodium ions, and so these sodium ions right here, Na plus, Cl minus. So these interact. The structure of the solid is held by these strong positive, negative, attractive forces. So there's a lot in there, and they form this very strong network. And that's why it gives the solid such its strong feel, strength of the material. So that's why they form solids really well. They're closely packed and they have these strong ionic bonds here. So this is what we call crystal lattice. We might not talk much about these types of structures unless we get to it at the end of the semester. But this is just an example of what some solids look like, especially crystalline solids. So crystalline solids are very ordered solids. You see here, you see in this example, we do have very solid, very ordered materials here, right? See these materials here, it's very structured, right? It's like a pattern. You have a gray sphere, gray sphere, green sphere. See gray sphere, green, green. So it's very ordered. When something's ordered like that, that's a very crystalline solid. So, and a crystalline solid, based on one of their properties, they can interact light frequently, and they look very lustrous or shiny, and that has to do with the ordered structure here. And you see here in this type of structures, you can see kind of these openings between the layers of the spheres here, and that opening I think gives allows passages of light to go through, and that what gives it its crystalline, or looks like crystalline crystals, the structure of it. So that's one of the properties of sodium chloride, ionic compound, very high melting point, even more so of a boiling point. So you can't really boil sodium chloride. What you'll get is probably plasma. So you'll convert it to plasma, which is basically ions in the gas phase, which is something we don't really typically think about, but it probably involves high energy particles in the gas, so that might be a dangerous thing to think about. Okay, on the other hand, so let's go to the opposite end of the spectrum. We have oxygen gas. At room temperature, oxygen is a gas, right? You can actually liquefy oxygen. It actually becomes this really nice blue color here. and that has to do with the fact with oxygen's electronic structure. Um, it's a paramagnetic compound. That's why it has this blue color. But we'll talk more about that when we talk about electronic structure and the structure of the atom. So it's a gas at room temperature, -19 boiling point. Sorry, melting point is -219 and has a boiling point of 183. So it doesn't take a lot to enter the gas phase. And that's because the structure of oxygen, um, it's not very it's not as complex as sodium chloride, where you have this repeating pattern of ions in a crystal structure. Oxygen is like this. Okay. So usually we draw oxygen as like this. So on each oxygen atom, you see here, each of these pairs of dots represents a lone pair of electrons as the number of electrons in the valence shell, or the outermost electron level, energy level of the atom. For oxygen, it's tip for the oxygen we know based on what it does and the properties of the oxygen. This is its most likely structure, where it has a unpaired electron on each atom, and that unpaired electron is what causes some of its unique properties and its reactive properties. So as you can see here, oxygen has no negative or partial charge on it. So it's considered a non-polar compound, has no separation of charge. So oxygen is not very water soluble. That's because it's not really polar. And so you see this oxygen molecule, you could think, oh yeah, it probably doesn't take a lot to separate its molecules into the gas phase or into the liquid phase. So it probably doesn't want to stay as a solid pretty much, because there's really no interactions oxygen can do to interact. So oxygen there is what we consider a covalent compound. There's no ions and there's just a single bond. And whereas sodium chloride, we would draw sodium chloride like this: sodium plus, Cl minus. So you see here, they are attracted by the positive and negative charges, no discrete sharing of bonds. Oxygen, however, does share its electrons right there. And to draw out the full shell of chlorine, we have to put up all 8 electrons to ensure that it does have a negative charge. Okay. So let's go over now chemical formulas. Okay. So I'll work on this example and then I'll stop the video here and then we'll continue on to the next one. Okay, so at the end of this page. So chemical formulas, a way to represent compounds in writing and communications. So it's important that we know how to write these molecules. Chemical formulas, they're very important in how we understand chemistry and communicate chemistry. Okay, so what is H2O2? Well, we call this hydrogen peroxide. So a very common household chemical, very good oxidant. So what this formula says, it has 2 hydrogen atoms and 2 oxygen atoms. And we can represent this structure as H. So when we draw this structure, we have to think about how it's bonded, and it's bonded like this: HOOH. So you don't have to draw it that way, but what's important is that this molecule has what we call a oxygen-oxygen bond, and we know that oxygen bonds, they are not very stable. They are weak and they are reactive, and that's what makes hydrogen peroxide so reactive. It'll react to break that OO bond because it's very weak and it's very easy to cleave it given the right reaction conditions. So that's why in hydrogen peroxide, you usually need to store it in a bottle that can't let light through, because if light were able to hit the hydrogen peroxide solution, it'll make it decompose. So very reactive, a very reactive species here. I work with hydrogen peroxide actually in lab as far as research, and yeah, it can do some interesting chemistry, interesting oxidation reactions, or what we call like reactions that basically add oxygen to a molecule, causes um maybe cleavage of some bonds. So it's a very good oxidant. It's very green too, so it's very safe. We use it in our house as we use it probably every day as an antiseptic, as a cleaning agent, etc. So very important molecule. All right, so we'll end this video here, and we'll move on to the next one, where we'll talk about more chemical formulas, especially how we usually draw chemical formulas in different disciplines of chemistry, or how you may see these formulas depicted, in media, in the text, in news, in printed material, etc. All right, see you in the next one. Do, 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 do.